Hello friends, a warm welcome to all the Wisdom Jobs viewers. In this video, I am going to teach you about what are forward reactions and what are reverse reactions and what are reversible and irreversible reactions. And of course, I am going to introduce you the next topic, which is law of mass action. Before going to all these topics, I am requesting you to please do subscribe to our channel wisdomjobs.com and please do get the updates, because we are going to post very important videos which are containing very important topics in the exam point of view. And so I am requesting you to please do subscribe to our channel wisdomjobs.com. Now let me enter into the topic. Now today's topic is what is equilibrium and what are forward reactions and what are reverse reactions. Now if you observe, the two types of reactions are reversible and irreversible. So we have already studied about this topic in the last video. Now in this irreversible reactions, there is no possibility of equilibrium. Okay, why? Because equilibrium will be existing in those reactions in which there is equal amount of products formed and equal amount of the reactants which are formed from the products. That is, if a reaction is favoring both the forward reactions and the backward reactions, such a reaction can be giving you a chance for equilibrium. So when can I say that in a reversible reaction equilibrium has occurred? Equilibrium is occurred when the concentration of the reactants and products do not change with time. That is, there is a time for which the reaction takes place from reactant side to product side and product side to reactant side. So after some time, every product and reactant gets settled with some amount. So the settling time, after the settling time, the reactants concentration and the products concentration will remain constant. So in whichever stage this constancy of the products and reactants are maintained, such a state we are going to call, or such a moment we are going to call it as equilibrium state. So when can I say that equilibrium is achieved in a reversible reaction? When the concentrations of the reactants and when the concentration of the products are same and they won't alter or change further, such stage we call it as equilibrium reaction. Now let me go to the next characteristics. So how can I detect whether the equilibrium state is being achieved or not? So first of all, we need to, the first and foremost condition for getting equilibrium or achieving equilibrium is we need to perform the reaction in a closed boundary or a closed surface. We cannot open it everywhere, so that's why it is to be done in a closed boundary. And after that, what are the different parameters by which we can say that equilibrium has achieved or equilibrium is occurred? Is there is a constancy of some properties of pressure, concentration, density or color. Okay, now when the products and reactants have got the are maintaining the same color of the precipitate or same pressure, okay, or same concentration, then I can say that equilibrium has been achieved. And the third point, third characteristic of equilibrium is that the forward reaction and the reverse reaction both are supporting the equilibrium. So we can say that equilibrium can be achieved either from forward reaction, or from reverse or backward reactions. Okay, so it can be achieved both by favoring the reverse reaction or the forward reaction. Now the fourth characteristic of an equilibrium is that it can be expedited, or expedited is nothing but what do you mean by expediting? Is it is to make it rapid. Okay, the rapidity or velocity of the reaction should be increased. That means instead of taking a longer time, in a shorter time the reactions and the products will form, okay, or the reactions takes place in a shorter time when compared to a longer time. So that's what that means. I can say that expedite or accelerate the reaction. Accelerating means what? Making it faster in time, or in a less time the reactants or products will be formed. So the fourth property of equilibrium is that the formation of equilibrium state can be expedited with the utility of a catalyst. Now we say positive catalyst. What do you mean by positive catalyst? Do we have a negative catalyst? Yes, we do have a negative catalyst. When we wanted to take less time, or when the reaction should be completed in less time, we use a positive catalyst. When the reaction should take more time, then we use a negative catalyst. So in order to accelerate the reaction, we use a positive catalyst, and in order to retard or decelerate the reaction, we use a negative catalyst. So we are going to use a positive catalyst, and the relative concentration of the reactants and products does not change irrespective of the catalyst. That means catalyst, what is the purpose of the catalyst? It can only accelerate the reaction rate of the reaction. It cannot alter the concentrations. So if I'm let me say one example, NaCl plus, let me say let me take a reversible reaction like this. So N2 plus O2, yeah, let me take a reaction like this. N2 plus O2 will give rise to 2NO. Okay, so if I'm having, let me say 1 mole, and here it is, let me say of course 1 mole, and here you have got formation of 2 moles, right? Now here the catalyst can form the nitrous oxide at a faster rate when compared to the without the catalyst. So without the catalyst, let me say it is taking some 2 seconds or 3 seconds, and with the use of a catalyst it will take, let me say, 1 second. So what's happening here? The time taken is reduced by the use of catalyst, but there is no altering of, or there is no modification or change in the concentration of either of the reactants or products. That is an important point actually. So next, the fifth characteristic of your equilibrium is that it is dynamic. That equilibrium concept is very much dynamic in nature. That means in given time, both the forward reaction and the backward reaction will be simultaneously carried away in the container in which the reaction is going to take place. So it can be either a homogeneous mixture or a heterogeneous mixture, but the equilibrium is favored by both the forward reaction and the backward reaction simultaneously in the same time. That's what is the basic meaning of your basic property of your equilibrium. Next comes, let me explain you some of the reactions here. So we have got two types of reactions, which is homogeneous reaction and heterogeneous reactions. Now if I am having only all the reactants and products in the same state of matter, so that means what are the states of matter we have? We have got solids, liquids and gases, is it not? So if the products and reactants, if both are in the same state of matter, that means if both the products and reactants are gases, as in this case. So if you take the first two examples, it is having both of them are gases. Okay, coming to the second third example, that is the formation of ethyl methyl ester from acetic acid and ethanoic acid is of course with the formation of water, is an example of a same state in liquid state. Okay, so these two are gaseous homogeneous reactions. Okay, and these are of course all are liquids, so they are in the liquid state. Okay, so what are homogeneous reactions? If both the reactants and products are in the same matter state or same state of matter, such an example I can call it as the homogeneous reaction. Obviously what is heterogeneous? A mixture. So if you take one example of heterogeneous reaction, okay, so of course here you have got one more concept to be dealt. If you take delta N, what is delta N actually? Number of moles of products minus number of moles of reactants. Okay, so in the first case there is in the second case, if you observe, here it is 2 and on this side it is only 1, here it is 4 and here it is 2, is it not? So what is happening here, PCl5, that is phosphorus pentachloride, is disintegrating or decomposing into phosphorus trichloride and chlorine gas, is it not? So here on the reactant side you have got 2 moles formed, and on the product side, so reactant side, we have got only 1 atom of or 1 molecule of phosphorus pentachloride. So obviously delta N in this case is how much? Delta N is equals to 2 minus 1, which is 1. And in the second case, the disintegration or decomposition of ammonia into nitrogen and hydrogen, here also we are going to get delta N is equals to 2. How I got 2 actually? 4 minus 2. So how 4? 1 plus 3, and here this side it is 2, so it is 4. So in this way I can calculate delta N, which is the difference in moles of products and reactants. So this is an example of delta N positive. Now in the third case, if you take, delta N is negative here. How it is negative actually? If you observe, in this case delta N is minus 2. How it is minus 2? 2 minus of 1 plus 3, so which give you 2 minus 4, which is minus 2. So in this second case, delta N is equals to minus 1. How I got minus 1? Because on the reactant side you have got 2 molecules of sulfur dioxide and 1 molecule of oxygen, and on the RHS you have got 2 molecules of sulfur trioxide. So obviously delta N is negative in this case. So if you observe, in the previous case delta N is equal to 0. So if you take all these 3 examples, delta N is equal to 0. That means there is no change in the number of moles. So if you observe the first reaction, delta N is equals to 0. How? 2 minus of 1 plus 1, which is 0. And in the second case also, delta N is equals to 0. Why? Because on the reactant side also 2 moles, on the product side also it is 2 moles. So obviously delta N equals to 0. So of course here also same is the case. Okay, delta N is equals to 0. So let me explain you the next concept, which is law of chemical equilibrium, or it is law of mass action. Now this law of mass action is very, very important in the exam point of view, because based on this law of mass action we are going to work out the problems in the forthcoming videos. So you should know, you should have a clear cut idea of what is law of mass action. Okay, now before going to law of mass action, I should introduce a new term called as active mass. Okay, so what is active mass is, I'll tell you. Active mass is proportional to concentration. Of course, generally whenever we come to concentration, the measure we use or the measure we take into consideration is generally molarity. It is molarity. Of course, in solutions you know what is molarity of a solution. Okay, and here since we have got a proportionality, I need to introduce a proportionality constant. So active mass is equals to some constant into molarity, or directly I can take K equal to 1. So active mass is nothing but its molarity. Okay, it's molarity. Okay, now that's what I'm saying. The proportionality constant is assumed to be unity. Okay, so for dilute solutions we take the proportionality constant to be equal to unity. So obviously the molar mass A. So what is this? What does it indicate? Inside the square brackets, if I am putting A, so it is what? It is molar mass of A. It is what? Molar mass of A. Similarly, if I say B in brackets, what does it indicate? Molar mass of B. Similarly, what is C? Molar mass of the compound C. So in that way I can represent the molar masses. So if these are the molar masses of the products and reactants, so let me take the equation as A plus B forming C plus D. So for this reaction, now the rate of the forward reaction. So what is forward reaction? A and B gives C and D. So the forward reaction rate is given by this formula. So rate of forward reaction is proportional to molar mass of A and molar mass of B. Now here I am not considering the number of moles as something else other than 1. Here both A moles are 1 and B moles are also 1. So when both the moles are 1, of course in the later point I am going to discuss you when the moles are also different. So here in this example I am taking moles of A and B as 1. Okay, so when A and B moles are 1, then the rate of forward reaction is given by the product of the concentrations of A and B, or the molar masses product of A and B. Now coming to the reverse, so if I wanted to remove this proportionality, I introduce a proportionality constant. So rate of forward reaction would be what then? So I am introducing the constant as Kf. Okay, where Kf is what? It is the equilibrium constant in the forward direction. So Kf into A into B. Okay. Now, in a similar way, rate of reverse reaction would be, it is Kb into C into D. Okay. So what is the C? Molar mass of C. And what about this D? This D is molar mass of D. Okay, molar mass of D. Now, in terms of the molar mass of C and D, what is the rate of the reverse reaction or backward reaction? Instead of reverse, I write backward. So rate of backward reaction is Kb into C into D, where Kb is what? The equilibrium constant of the reaction in backward direction. So based on, now since both are equal, what is that both are equal? The at equilibrium, since both the rate of the forward reaction and backward reaction are equal, I can equate this. Okay, so what? How can I equate it? So rate of the forward reaction is this one on the LHS. So this Kb into C into D represents the rate of the backward reaction. So obviously the rate of the backward reaction is equals to rate of the forward reaction at equilibrium. So based on this assumption, I can take simply I can write it as Kf into A into molar mass of A into B is equals to Kb into molar mass of C into D. And obviously from this, Kf by Kb if I take. So from this equation, so if I consider this equation, let me consider Kf by Kb. So Kf by Kb, that we call it as a new term which is Kc. So what is Kc? Kc is the equilibrium constant of the total reaction. So Kc is equals to K by Kb, and from this equation, if you observe from the equation A, it is what? It is simply, I want Kb in the downward and Kf in the upward direction. So so it will be simply A into B upon C into D. Okay, C into D. So in this way, I can define the equilibrium constant of an equation of a reversible equation. Okay. So now the same constant, if I increase or if I apply to an equation or a reaction which contains unequal moles. So in the previous case, as I told you, I have taken the total reactants and products as 1 mole each. Why? Because A plus B gives rise to C plus D. That was the reaction I have assumed. Now instead of that, if I am taking some other equation like this, so if the reversible reaction is of this form, so if the reversible reaction is of the form M1A plus M2A2, sorry, M1A1 plus M2A2 so on and so forth up to MNAN. And on the product side, we have got B1, B2, B3, so on and so forth are the products, and with their respective moles as N1, N2, N3. Then the homogeneous reversible reaction is of the form this one. Okay. So for this reaction, what is going to be the equation for your equilibrium constant is, it is given by this equation, that is Kc. Kc is the equilibrium constant. Kc is equals to, now always the product should come on the up, that is in the numerator. So what are the products there? B1. So B1, all B's are products. B1 raised to the power of its number of moles N1 into B2, the active mass of B2 or concentration of B2 raised to the power of N2 into so on and so forth divided by that of the in the denominator, what I told you, in the denominator the reactants comes into picture, of course respectively raised to the power of their number of moles. So what are the number of moles in the reactant side? It is M1, M2, M3, so on and so forth. So A1 raised to the power of M1 into A2 raised to the power of M2, so on and so forth. Okay, so in this way equilibrium constant can be derived for any reversible reaction. I feel you have understood this concept of equilibrium and equilibrium constant thoroughly. So even then, if you have got any queries, please do express all your doubts or queries at the comment box which is provided at the bottom of the video. So I request you, please do subscribe to our channel wisdomjobs.com, because we are going to give you so many exciting topics and important videos in the forthcoming classes which you may miss. Okay, so thank you for watching this video and having your patience. Please do subscribe to our channel Wisdom Jobs.